Picking up right where we left off on the structure of our hydrogenic atoms and developing the radial wave function. Okay, so let's see here. So I've got the learning goals right here. So what I covered in that first lecture on this material, right? We briefly talked about the Rydberg equation. We built up the hydrogen atom Hamiltonian. I kind of went through the solution to the hydrogen atom Schrodinger equation, and it's something that we could have spent, weeks trying to grind out ourselves. But I just want you to be familiar with how it's solved, right? For those various boundary conditions, when L is equal to 0, when L is not equal to 0, when R is close to the nucleus, when R is far from the nucleus, etc. Okay? And then that's about as far as we got. And now what I'm going to pick up with today is more on this radial wave function, nodes, and then we'll start to get into the specification of orbitals, which is going to be really cool. Okay, so to just kind of remind you where we left off here, we had these condition-specific solutions to the radial wave function, right? Dominant. When close to the nucleus, this polynomial, the Laguerre polynomials that bridge the two regions when the electron's close to the nucleus and when the electron's far from the nucleus. And also, what I think I didn't mention last time, but in these radial wave functions as well, we have to, of course, include a normalization constant. Normalization. Wow, I really screwed that one up. Okay, let's try again. Normalization constant. And that normalization constant is dependent on quantum number n and L. And if you recall last time, the Laguerre polynomials establish the dependence of L and n, right? We know n just takes on integer values, 1, 2, 3, 4, 5, etc. And L takes on values 0, 1, all the way to n minus 1, okay? So recall, if n is equal to 1, then L can only be equal to 0. However, if n is equal to 2, then L can be equal to 0 or 1, right? If n is equal to 3, L can be 0, 1, or 2, etc. Okay? And so this function, this nomenclature we're going to see, R in L, my radial wave function, so it is normalized in the sense that R squared times R squared dr equals 1. So remember where this extra R squared comes from. It comes from d tau. And so we neglect the sine theta, d theta, d phi because our radial wave function is only dependent on R. Okay? So moving on, here are the radial wave functions for a given set of quantum numbers. Okay, so this is getting really cool. So if we look at this now, and so once again, there's a bunch of collection of constants, right? Rho is 2zr divided by Na, where A is the Bohr radius, and right is a collection of all of these constants, okay? Which we know gives us 52.9 picometers. All right. So this is just kind of giving you the full nomenclature of the radial wave function again. And then also the energy solution to the radial wave function is given here. And we're going to explore that in more detail. But what's important to note is it's inversely proportional to n squared. Okay, so remember that. Inversely proportional to n squared. We're going to see that graphically. Okay, so now if we kind of just peruse and take a quick look at these radial wave functions, so we can see when n is equal to 1, L is equal to 0, we call that the 1s orbital, right? This is that radial wave function, okay? And so it looks a little funky, but as you can see what I've got here to my right, this is that very first wave function that we played with during the Math 2 assignment, I believe. Okay, so it doesn't quite look the same, and I'll tell you why momentarily. But what's important to note is it's pretty close, right? We're starting to see where that a to the 3/2 power comes from, right? There's my a cubed, and then of course it's all square root, so it's 3/2 power. And then we've got e to the negative rho divided by 2, which is really just going to be e to the negative zr divided by a, and there it is, right, for 1, 0. Okay, very cool. So now as we move on to the 2s, 2p, etc., you can see the radial wave function does get a little more complicated. And that's all right because we have them all tabulated here for us. Okay. So let's take a look at what these plots look like. So here are a graph of all of the radial wave functions. All right. And so right here is my 1s orbital, this just decaying exponential, okay? When we look at n is equal to 2, L is equal to 0, here's my 2s. And let's just keep going with that. N equals 3, L is equal to 0. Here's my 3s. And now n is 2, L is 1. Aha, that's my 2p, okay? N is 3, L is 1. There's my 3p. And n is 3, L is 2. That's my 3d. Okay, so what about nodes? Well, let's highlight here specifically where this crosses 0. Okay, we already remember that our total nodes was given by the particle in the box problem, and that's n minus 1. Okay, so if we now start to kind of play with that, right, when we look at the 1s orbital, we see 0 nodes, and that makes sense because 1 minus 1 is 0. Fantastic. What about 2s? Okay, well, if I look at where this crosses right here, okay, look, there is 1 node. So we can see with 2s, let's just tab these down, right? So 1 minus 1 equals 0. And so now over here, 2 minus 1 equals 1. So there's our node, all right? So let's just keep going this with 3s. Now I know maybe my marker just covered it up, but there are 2 nodes. There they are, okay? And so that goes as, let's see, 3 minus 1 equals 2. But now when we go to 2p, because it's n is equal to 2, we should expect to see 1 node, but there's 0 nodes in there, okay? And then similarly with 3p, if you look at this now, there's only 1 node, but maybe we expect it to be 2, okay? So as it turns out now, we have total nodes, and we also have this thing called radial nodes. And so the radial nodes are only observable on the radial wave functions, okay? So radial nodes actually goes as n minus L minus 1. And so now if we go to this 2p situation, my n is equal to 2, my L is equal to 1, minus 1 equals 0. Okay, 0 nodes. And so same with 3p now. We have a 3 minus 1 minus 1, and that's going to equal 1. So 1 radial node. And then now with 3d, right, it's 3 minus 2 minus 1 equals 0, so 0 radial nodes. Okay. So now how do we connect the total nodes and the radial nodes? Well, the last type of node we have is called an angular node. And just to remind you, right, nodes are regions where the wave function equals 0. So that's where we expect the electron to not exist. Okay. So we're not going to observe angular nodes on this radial profile. We have to look at the theta phi YLM spherical harmonics, right? We have to look at the full three-dimensional picture to get the angular nodes. But as it turns out, angular nodes are total minus radial. Okay? So, for example, let's see, are there any here? So these are all showing me pretty good stuff. Aha, so let's talk about 3D for just a second, right? So we got 0 radial nodes, okay? except for the fact that its n is equal to 3, it should have 2 total nodes, the 3D. But now we can recognize, because it's 0 radial nodes, we know that 3D will have to have 2 angular nodes, and we're going to have to observe those on an angular graph. Okay. Same with the 2p, right? There's 0 radial nodes, but there should be 1 total node because its n is equal to 2. So that means 2p only has 1 angular node. 3p is going to have 1 angular node and 1 radial node, etc. Okay. So let's keep moving forward with that. And now let's put together our full 1s wave function. Okay? So my nomenclature is going to go as follows. I'm going to write it as psi 1 0 0. And so that stands for I'll write that up here. So psi n l ml. That's how we're going to put together our total wave function. All right? And so I know that I can break that up into r of 1, 0, right? R of NL. And I can also then break that up because I know that y is, YLML. So that's going to be y 0, 0 of theta and phi. Okay? And just to remind you, right? In this chapter, we spent a lot of time, that whole first lecture, just developing this radial wave function. In chapter 8, we already came up with these angular wave functions. The rotational, right, wave function, the spherical harmonic, that satisfies our rotational component. We've already done it, right? And if you recall, I gave you this big table of spherical harmonics. So here I'm just kind of zooming in on the shortcut here. And so if I put this together now, right, I'm going to say psi 1, 0, 0 as a function of r, theta, and phi. So my r 1, 0, I'm just going to put it together in all its glory. I'll remind you that rho is equal to 2zr over na. So that's 2zr over na. And because n is equal to 1, right, I can put that in there. I'm going to leave the z as plus 1. Or excuse me, I'm just going to leave the z as z. But we recognize that for hydrogen, z is equal to 1. Okay, so when I put that in, I've now got a 2 times the square root of z cubed, all divided by a cubed, times e to the negative rho divided by 2. Okay, and so follow with me here. If n is equal to 1, that means my rho is 2zr over a naught. But look, in the exponent, it's rho divided by 2. So that's going to cancel my 2. So that's now e to the negative zr divided by Bohr radius. And then now, so that was just my radial. Now I have to add my spherical harmonic, right? So I'm going to say this times now the square root of 1 over 4 pi. So now if I do some algebra on this thing, I know that I can pull out the, let's see here. Yes, I can pull out the 4 out of the square root, and that just becomes 2. Okay, so that's going to eliminate with this 2. Oops, we'll do a different color so you can see my algebraic manipulations. So that cancels with that. Lovely. And then now I can just put that pi into the square root, and I can write this function as the following. So that's going to be, let's see, square root of z cubed over pi a naught cubed e to the negative zr divided by a. Fantastic. I have this written somewhere else. I just want to make sure that, so I didn't write z cubed up here. Why did I not do that? I have to think about that for a moment here. I think that might have a mistake on there that I've forgotten to do z cubed. Oops. Because you notice that's what I'm talking about in my Mathematica file, right? I forgot to put z cubed there. Okay, so we know it's not going to change it for, we know it's not, oops, retry. It's not going to change my result because for z equals 1, right, it doesn't matter, but let's put it in there to be complete. And there we have it, right? We've got our psi 100, which we know is our wave function for our 1s orbital. Very cool. And we can put together all of the other wave functions for 2s, 2p, 3s, etc. By calling up the correct radial wave functions and spherical harmonic wave functions. Sweet. Okay, so let's keep moving on, all right? So the specification of orbitals, okay? So N is our principal quantum number, and that determines the energy of an electron in a bound state, okay? So electrons exist in orbitals with quantum numbers L and ML, and those specify the angular momentum of the electron-proton pair, okay? An electron in an orbital with quantum number L has angular momentum magnitude, right? Total magnitude root L times L plus 1 h bar, where we know L can be 0, 1, 2, all the way to n minus 1. Also, an electron in an orbital with quantum number ML has z component angular momentum ml h bar, where now ml takes on all values 0 to plus or minus L. Okay. Additionally, electrons possess intrinsic angular momentum from their spin. Okay, right? So electrons are spinning round and round while they're orbiting the nucleus, much like our sun, moon, planet Earth system. Okay, right? Ms h bar on the z component and total magnitude root s times s plus 1 h bar. And overall, we need NL, ML, and MS to specify a complete bound state. And when we're using this term bound state, we're really referring to an electron within an orbital, our classic view of chemistry. Right? Not even of physical chemistry, just chemistry in general, right? Our electron in an orbital is a bound state described by N, L, ML, and MS. Okay, very cool. So let's move on. So now let's look at the energy solutions, okay? So and this is just the solution to the radial component. Which is all we need to solve the energy solution because you can see it's only dependent upon n. And what's important to note, it goes as 1 over n squared. Okay? So for example, if I look at, this is n equals 1 right here. Okay. Then we view that, right, here's the negative sign, right? Remember, E sub n is less than 0 for all bound states. And there we've got that negative sign, okay? So if I keep going with this and kind of make connection to the Rydberg equation, right? Here we can see that so I'm going to start over here on this side, okay? Rydberg's constant for any nucleus. So this is what this means. This is Rydberg for any type of atom, okay? We get this constant. It's a collection of all of these constants that you see in this energy solution, right? E to the 4th power, the epsilon squared. There is this, h bar squared and h, and I'll describe why those are just slightly different, why we've got the product h and c. I'll describe that momentarily, okay? So now the Rydberg constant for hydrogen, right? Rydberg for hydrogen comes by ratioing the reduced mass for hydrogen versus the mass of an electron, which they're very close. So RH is very, very close to this R infinity because the reduced mass of hydrogen is just basically equal to the mass of an electron, right? Our reduced mass of hydrogen is Me times MP divided by Me plus MP, okay? And so now what we have right here is this is RH in terms of joules, okay? And if I multiply it by HC, then I'm going to get my solution in wave number. Okay, so just taking that joule, which if we work through all those constants, right? And so that's actually more directly comparable to the energy solution, right? There's mu e to the fourth power divided by 32 pi squared epsilon squared h bar squared. And the n has been taken out because remember, my Rydberg can be described by saying 1 over n squared, right? Multiplying this result by hc is what gives it the wave number unit. And so this R infinity, the hc was divided out by the other side. And so that's why the pi gets eliminated, and that's why it becomes h cubed over c, or h cubed times c, okay? I don't want to dwell on that too much longer, just to point out that this Rydberg equation that we talked about at the very beginning, where I made a point that our goal is to be able to predict this thing, well, here we have it, okay? We've done it. So now, the way that we could view this, because we have, this RH is a collection of all these constants, and of course this HC, like I said, it's just going to give the solution wave number, right? We could drop the HC if we wanted the solution in joules. So now what you can see, because it's n squared, when we get n is equal to 2, this reduces the energy by a factor of 4. And when we have n is equal to 3, this reduces the energy by a factor of 3. And when I mean it reduces the energy, what I'm really referring to is it reduces it from the 0 level. And so what that means now, I should really be drawing these as up or down. And so what that means now is as we get up higher and higher in levels, we get closer and closer to this continuum of infinity. And so this is why we use this R infinity, because this whole giant arrow that I just drew is roughly equal to R infinity. Technically it's RH, but again, we know RH is equal to R infinity. And that's because that describes when n approaches infinity, then our hydrogen atom becomes ionized, okay? So this shows us the depth, the full depth of our bound state. So this is very cool. So we can calculate the ionization energy of hydrogen. It's the Rydberg constant. But also when we reduce, that by the 1 over n squared, we get all of these different energy levels, okay? And as you all hopefully remember from Gen Chem, right? When we calculate this delta E, that's going to give me the energy between each successive level, right? Which describes the type of light that we might get as this electron moves up and down through the levels. Okay, so to come full circle, I'm going to go all the way back to my first slide here. Right? So those Balmer lines are given by transitions amongst the n is equal to 3 and 4 and 2. Okay? These Lyman lines are typically given from n is equal to 2 down to n is equal to 1, and some are some are 3 to 1 and some are even 4 to 1. But what's important is the Lyman describes everything going all the way down to n is equal to 1. The Balmer describes everything going down to n is equal to 2. And the Paschen line describes everything going down to n is equal to 3. Okay? And the bracket line shows everything going down to 4, but we don't have that on the diagram. So that's awesome. So we did it. And what's kind of amazing, what's really cool about this is if we were to compare the energies we calculate from this Rydberg equation to what you actually see in a spectra, it is amazingly accurate. Crazy accurate. And it works really, really well for hydrogen and only hydrogen. And we're going to start to see why this immediately fails when we try to describe the same model with helium. It fails. We can no longer do it. Okay, so let's see what I got next. So this is kind of where we're going next, the description of shells and subshells. And since my last lecture was kind of long, I'm going to cut it off here. So we went through those hydrogenic radial wave functions and how to apply them given a set of quantum numbers. So basically what I mean by that is how do we construct a wave function for a given orbital given knowledge of the radial wave function and the spherical harmonic wave function, right? Put it all together, okay? So know how to calculate total nodes, radial nodes, and angular nodes. We went through that, okay? And then where I'm going to pick up on the next lecture is going through the specification of orbitals, shells, and subshells using quantum numbers. I already kind of briefly talked about the specification of orbitals with that kind of list of things I was going through. And what's coming next is a discussion of shells, subshells, SPD orbitals, right? This is all going to get to that nice, lovely, familiar ground from Gen Chem. Okay, exciting stuff. I'll see you later.